Like electric potential energy, voltage is not a vector, so multiple voltages can be added directly, taking into account whether they're positive or negative. Also, like gravitational potential energy, voltage is not an absolute value. It is compared to a reference level. We've already assumed a reference level for potential energy to be 0 at infinity, so let's do the same thing for voltage. We'll assume that at infinity, voltage is equal to 0. Because of that, we can assign a specific value to voltage in calculations. The next slide will continue this gravitational analogy to help you understand the concept. If you're in the Boy Scouts or Girl Scouts or did some camping or hiking at some point, hopefully you'll remember a topographic map. This is a map that has these lines on it. These lines tell you how high you are above sea level. The area between the lines shows that you're changing height from, let's say this is 10 meters and this is 20 meters. If you have a very big space between the lines, that's a very slow change in height. That's a very easy thing to walk on. A little space between the lines means there is a very quick change in height, a big incline. So where in this picture is the steepest incline? Well, let's look. Is it over here? No, you've got a lot of space. This is water, that's kind of flat. How about up here, near Keith's Dome? See how close these lines are? That means that you have a very short distance between the height change, so that is going to be your steepest incline right there. Here's where the analogy comes in. These topography lines, the lines of equal height above sea level, we're going to call them equipotential lines when we use them to represent electric potential. An equipotential line means anywhere you are on that line, the electric potential is the same, it's equal, hence the word equi there in equipotential. The closer the lines are together, the faster the change in voltage. And the faster the change in voltage, the larger the electric field. So if you look here at this hill, and we're going to call it a voltage hill, you come up here, that's pretty even. You don't have a huge slope there, and the lines, if you project it down here, are far apart. You can see there's a big difference from 0 to 50 to 230, so this would be easier to walk. You'd also have a smaller electric field there with the analogy. On this side, it's very much steeper. The voltage changes quicker and you'll have a stronger electric field in this area. So strong electric field, weak electric field. Weak, strong. So much for the analogy. Now back to voltage. These green circles here are equipotential lines. Recall the expression for voltage is just K, Q, over R. So if I have a positive charge Q here, the voltage at any point has a 1 over R dependence. That means if you're the same distance R away, you have the same potential. So when you connect all those up, you get an equipotential line. We're going to make a statement now. The electric field lines, which are the blue lines, are always perpendicular to the equipotential lines. The electric field lines are farther apart when the equipotential lines are farther apart. So you can see here the distance between these two field lines much greater than here, and the equipotential line here is further than that. Now, you know why the field lines are going that way. We've done that before in the electric charge section. They point radially away from a charge. We also now know that the electric field lines points from high to low potential. The further you get away, the lower the potential. So we know that just by drawing the picture, but why are the electric field lines always perpendicular to the equipotential lines? There's an actual more physicsy way of looking at that. Discuss that within your groups and then go to the next slide. Equipotential lines, these green circles, represent points in space where the electric potential or voltage is the same. If the voltage is the same, that means the electric field along this line, tangent to this line, anything that would cause a charge to move along, must also be 0 because we define the electric field lines as pointing in the direction of decreasing potential. Potential is not decreasing here, it's staying the same. Therefore, the electric field must have no vector component along the equipotential line, hence it will be perpendicular at all points. We'll come back to this later on in this chapter and we'll actually give a nice equation for the electric field and the voltage relationship. For a positive charge like this one, the equipotential lines are positive. What I mean is, for example, this line might be 100 volts. This line could be 80 volts, this circle. This line could be 60. And they're all plus. Okay, that's just the reference frame we're using. And the further you go away, this would eventually go down to 0 volts at infinity. A negative charge would be surrounded by negative equipotential lines. In that case, this would be negative 100, negative 80, negative 60, and so forth until you get to 0 at infinity. More interesting equipotential lines, kind of like the topographical lines on a map, are generated by more complex charge configurations. This configuration is created by a positive charge to the left, because you can see what's happening here. You start at 20 volts and it goes down to 10, then it goes down to 0. But wait a minute, this isn't infinity. No, because there's another charge. So let's say there's some kind of negative charge configuration over here. Negative 20, negative 10. And what happens in the middle is you add the voltages up due to these two charges and they cancel out and you get 0 volts. So in this case, you don't have to go to infinity to get 0 volts. You've got the effect of these two potentials canceling out right in the middle. Note the signs of the equipotential lines. Positive near the positive charge, negative near the negative, and it approaches 0. And also notice the electric field vectors. They are always perpendicular to the equipotential lines. And again, goes from positive to negative, so you can see all the arrows are pointing left to right. The work done by an external force to move a charge from infinity to a region of space with an electric potential of V has been shown to be W work equals QV. This assumes that the electric potential at infinity is 0 volts. However, in this case, we have a 0 volts right here. So what happens if we move a charge from point D on the negative 10 volt equipotential line to point B, the equipotential line for plus 10 volts? For this case, unlike the voltage at infinity, which is 0, both of these points have a non-zero value for voltage. So we need to find the change in electric potential to find the work done by an external force. So that would be Q delta V, where delta V is V final minus V initial. If we have a positive charge moving from point D to B, that means it's moving to a higher electric potential. It goes from a negative 10 to a 10. We sort of anticipate that positive work must be done by the external force, just like lifting a mass in a gravitational field. Let's see if the equation bears that out. Work is Q delta V, Q is positive, Vf minus V0. Vf in this case is 10 volts, V final is negative 10. We do the math and we get the work is 20 times Q in volts. And of course what we have here, Q is positive, so 20 times a positive number, we have positive work. What if we have a negative charge moving to a higher electric potential? In this case, we're going to anticipate negative work must be done by the external force. Let's see what happens. The equation is work equals Q delta V. We put in a minus here because it's a negative charge, and we still have Vf minus V0. Vf is 10, V0 is minus 10, so we carry out the math, and we come up the work by an external force is negative 20 Q volts. In this case, Q now is the magnitude, so it's positive. 20 is positive, this negative sign tells us that we have negative work done on the charge by the external force.